Right, it seems to be working, so let's get going. Hello everyone, I'm Simon Mack. I'm the CTO of Natural Motion, and what I'm going to be talking about today is a couple of the newer features that we've put into our Morpheme animation system, in particular parametric blending and full body IK. But what I want to do is actually go right back to the very basics of explaining about blending, animation blending concepts, before moving on to how we've added the parametric blending system. And I'll do the same thing with IK as well. So I know some of you will have seen Morpheme before and you'll know all about this. So some of the early sections might be a bit basic, but I think it's very important for everyone to get a full understanding of these systems. And as well as talking about these things, what I'm going to be doing is demonstrating them to you in Morpheme. So Morpheme is Natural Motion's animation system. It's a runtime animation SDK that you integrate into your game to power your character animation. And in addition to that, it's an authoring environment which allows you to visually control how you use your animations at runtime in the game. So I'll be showing you version 6 of that as we go. And again, for the people that have already seen Morpheme, you'll be seeing some of the new user interface that we've put into version 6 and some of the new features in there as well. So let's start at the beginning and talk about blending. So blending is just about when you use more than one animation at the same time. So the simplest way of using animation in your game is you play back one animation clip and then you switch to another one. So when your character needs to go from jogging to running, you stop playing the jog, you start playing the run animation. But that just never looks good. So what you normally want to do is actually try and mix your animations together. And that's what we mean by blending. And this isn't any kind of magic. It's actually a really simple idea in that all you do is take for your output frame is just a mixture, a weighted average of two other input frames. So you might have in one animation clip at one frame, you might have, say, this angle in the arm. The other one, you might have this angle. And a blend is just somewhere between the two as a weighted average, a certain percentage of these two animations added together. And that's all there is to it. And so at runtime, the interesting thing is that you dynamically control this input weight. So you can say what proportion of the information will come from one animation and what proportion will come from another one. And that's what gives you the control at runtime to create new animation results. So let's have a quick look at some very simple blending in Morpheme here. So this is our Morpheme user interface, and what I have here are just a whole bunch of animation clips. So let's first of all look at two animations I have, one here for the character jogging and another one for the character running. And what I want to do is just create a simple blend between these two animations. So I can simply take these animations, drop them into my blend tree here, and I will add a blend node here. So this will take, put these the right way around, take jog and run, produce the output, and what I'll do is add in an input control which will let me change the relative weight of these two animations. And then we look at the result. So you'll see here, now when my speed is at 0, we have the character jogging. And as I change the weight of that blend, we gradually move towards the character running. So if we look in a little more detail at what's going on, I can use our debugging facilities here and go down into slow motion. And what we'll see is when I'm here, you can see the white skeleton is our output, the green skeleton is our jogging animation, and the yellow skeleton is our running animation. When I'm at a very low speed, you can see the output is very close to the green skeleton, and as I increase the speed, that output becomes, first of all, an even mixture between the two animations, and then as I go further towards running, you can see the output contains more of the information from the run animation and less from the jog. And that's really all there is to the very basics of blending animations together. It's just a weighted average of the frames from each animation clip. So that simple example, I just have one input. So I have two animations and one input controlling the weight of them. Obviously, I could have had more than two animations. I could have 3, 4, 5 animations, and the input would just still control a weighted average of those, maybe 2 at a time or 3 at a time, all being mixed together. But quite often what you want is to have more than one input. In fact, you nearly always want more than one input. So you might want to control not just the speed of the character, but the rate at which the character turns as well. Now, you can't do that in quite such a simple way of just mixing animations, because you need to actually cascade the blends and create effectively a tree of these blends to combine the results together. So again, much easier to understand if I just show you. So what we have again is simple jog and run, but now I'm going to introduce the idea of turning. So I will find a couple more animations. I have the jog with the character turning left, so we'll bring that in. And I have the run with the character turning left as well. And I can bring that into the view as well. And then what we do is we first of all create blends based on the turning rate. So I'll add some more blend nodes in here. And what you'll see is I can blend jog and jogging turn left, which will be based on the banking of the character. And then I do exactly the same thing for the running side. So now what I have here is the output of this node will be a mixture of jogging and jogging turning left. This one will be an output, a mixture of running and running turning left. And I can simply mix those two results together based on the speed that my character's going. So now this gives me proper two-dimensional control. So here you can see I can now increase the speed of my character and make him turn more or less to the left, and everything mixes together properly. And again, the principles are very similar. If I look at the animations coming out of these, you can see that the green skeleton here is a mixture of jogging with its left turn, and the yellow skeleton is the same for running, and then our output is a simple average of those two based on the speed of the character. So it's the same principles, but you layer the system up to create more and more dimensions. And if we look at a slightly larger example, here I can find in this locomotion network an example where instead of having just 2 animations for each one, we use 3. So we're still having 2 dimensions here, but now I'm able to use walking, jogging and running with both turn left and turn right. So you'll see each of these is a blend based on the banking, and then I blend those 3 together based on the speed to give me my output. So now I can go all the way from walking to running, and I can turn left and turn right. And at each stage, you can see from the red highlights here, the blend nodes are just picking two animations, they're blending between them, and then the final blend node is picking two of those blends and blending between those. So again, it means that ultimately I'm just averaging out 4 animations in different combinations, and that's producing my result. And you can see I get a very, very smooth blend, very smooth mixture of animations. So before I move on to show you a whole different way of controlling that blend, which is the interesting thing really, I want to quickly mention time. So what I talked about as blending is just taking a frame, 2 input frames, mixing them together and giving you the output frame. One little subtlety is you need to choose how you're going to pick those 2 frames. So if all your animations are the same length, it's really easy. Your frame 30 of your output is the mixture of frame 30 from each of your input clips, and so on. It's really simple. But most of the time, your animations are not all going to be the same number of frames. And in that case, you need to think how you're going to scale these animation clips. So you can just say, well, we're going to shrink them all so they're the equivalent size. So if you have one animation that is 30 frames long and one of them that's 60 frames long, then you might take a mixture of frame 2 from the first one and frame 4 from the second one, and so forth, to mix them together. And that works if your animations all contain exactly the same information. So if you have 2 footsteps in each animation and they start on the same foot, that will work. A much better approach is to actually use markers on your animations and then synchronize the time between those marker points. So I will build a very simple example again to show you that in here. So we'll just blend first of all a walk and a jog. And we'll look at what happens with these source animations when I don't do anything with the time. So walk and jog, we bring these in and blend them together. So walk, jog, result, and add the input. And I'll turn off this node from being clever, and we'll just run that result. So now when I mix these 2 animations, you'll see I get strange little patterns here in the footsteps. And that's because these 2 animations don't actually have their footsteps happening at the same time. The animations are actually of different length. And you can see the markers here showing time going through the animations, effectively going at different rates. And what we can do is actually just mark up each animation. And you'll see we put these time markers in here that correspond to the footsteps in each animation clip. And those are actually the footsteps appearing on the result here. And what I can do is then tell our blend node to actually be a little bit clever, and what it will do is stretch time between those markers to keep the footsteps in sync with each other. So now you can see that each time the current position passes through these markers, they're synchronized. So the footsteps in my animations are synchronized as well, and you can see we don't have those blending problems. And in fact, it's even clearer if I, instead of having that simple motion, I bring in a limping animation where we have very uneven footsteps. And you'll see as I blend into a limp here, how time now moves in the walk. We move very slowly through the first part and very quickly through the second part of this animation, so that we're picking the right frames to join together in our animation blend. And I guess the really important part here is that you have essentially three different parts to blending. You have the selection of which frames you're going to join. So actually first of all, you have to choose which animations you're going to be blending together. Then you choose which frames from those animations you blend together. And then you choose how you mix those things. And these are actually all independent choices. You can make the decision on how to do these separately. So the way that you mix the animations together is always pretty simple. That's always basically just an average, a weighted average of the animations. The time I've discussed, the way you pick the frames, you can do very simply, or you can do with this kind of stretching. The way that you select the animations to blend is a more interesting problem. And what you've seen so far is using this simple tree structure. But there's a completely different way of doing this, which is called parametric blending, or what we call in Morpheme a scatter blend. So this is about picking which animations you're going to blend and what proportions of those animations you're going to use together. So think about this. You imagine a 2D graph, so like a grid, and each axis on that graph is an input. So you might have speed on one and turning angle on the other. And the idea is that you can place your animations in the positions that they correspond to on that graph. And then you build up triangles in the graph to say, if I'm inside this triangle, I'm going to blend these three animations. Again, much easier if I just show you. So what I'll do is build a new scatter blend, and we'll have this example again of the character being able to jog and run and turn left as well. So I'll bring in my input parameters, and I will now drag in our 2D scatter blend. And what I'll say is we'll have speed on the Y parameter, and we'll have our turning angle on the X. Okay, so I have my graph, and now I can again find my my animations that I want to use. So just quickly find those. So I will take my my jog, and I want to say that my jog is going to be 0, 0. So I'm going to define 0 means that I'm jogging, 1 will mean that I'm running. So if I bring in my run animation, I can take that, and now I can move that, so I'll put that at 1. So you can see our graph, we have 0 down here, 1 up here, so jogging to running. And then I'll say if I'm jogging and turning left, then I will move that across the other axis. And I will just make this look a little nicer in the editor, so you can see more what's going on. Right. Okay. And then I will put the run turning left at 1, 1. So the principle here is this axis going up is how fast we're moving. This axis over here is how much we're turning left. And then I can simply build up my blend space. So I can say if I want a value that's in here in terms of its speed and its turning angle, then we'll use a mixture of these three animations. And if I'm in this area, then I'm going to use a mixture of these three animations. So, oh good, my mouse has stopped working. Okay, this is going to get difficult. Okay, so let's have a look at this. So now you can see here when I'm at 0, 0, we've got 100% of this animation. and then as I increase my speed, you can see the proportion of these two animations changes as we go closer to running. And of course, if I change my banking, we can move across the other axis, and we've now got a mixture of these two animations. But of course, I can do both at once, and you can see here how at this position, in terms of my speed and banking, we just compute this mixture of animations. And we can move around like so. So this has a few big advantages over the tree approach. One of which is it's very simple now to understand. I can see all my faster animations are further up, the slower animations are lower down, the turning is over to one side. But also it's much easier now to think about extending it. If I want to also have turning right, well, it's very easy. It just goes on the other side. Over here, I can add my right turns. And I can move these around and extend it. And I don't have the problem that I have with the blend tree of always having to add more nodes and adding more complexity. It's always the same graph. It just has more triangles in it. The other thing you might notice is actually the performance at runtime is a bit better, because in this case, I'm blending just 3 animations instead of 4 animations to produce this result. So it can also be a bit more efficient that way. But it has another big advantage, and that comes once you start looking at motion analysis. So in parametric blending, normally those two axes that you look at actually represent physical properties of motion. So things like the speed that your character's moving, or the turning rate of the character. And those kinds of things tend to be what you actually plot on your graph. Those are what your inputs are. Well, it's perfectly possible using a tool like Morpheme to actually analyze the motion in each of your animations and calculate that value for you. You know, it's quite simple to look at an animation and decide how fast is my character moving during that animation. And then you can position it in the graph automatically. You can also, once you've got a whole range of these points, you can build those triangles automatically as well. And at this point, scatter blending becomes really powerful and really fast. So let's now build a more complicated example where I'm going to have, say, 9 animations to cover the character walking, jogging and running, and turning left and turning right. And this time I'm going to set the system up so that it will actually automatically analyze the motion for me. So I'll create my speed and banking, and once again I'll drop in my scatter blend. We'll put banking on the X, speed on the Y, and this time you'll see in the attributes I'm able to use these real physical properties of motion. So now I can select from a whole range of different characteristics of the motion what I want each axis to represent. So in this case I've got the turning rate of the character in degrees per second and the forward velocity of the character in meters per second on the other axis. And now what I'm able to do is just find my animations and drop them into that graph and have the system automatically look at the properties of those animations, work out how fast the character is moving and the rate at which the character is turning in each animation, and place them in the correct positions in the graph. So we drop it in, it's done the calculation, and it's looked at each animation and has figured out how fast it's moving and how much the character is turning left or right. I can tell the system to automatically build the triangles for me, and then if I want, I can just run it and move inside that space. And you can see now I instantly have a blend of the character moving forwards, turning left and right at all different speeds without having to build any kind of blend tree. and the system has just worked all of this out for me automatically. So there's some big benefits to using scatterblend, particularly with motion analysis built in. The first is it's just intuitive. You can look at the graph and understand what your animations are doing. You know where the character's running, where he's walking, and so on. Because it's done the analysis in real-world units, your inputs are in real-world units. So you're feeding in meters per second, degrees per second. It's no longer just a percentage of each animation. You're not feeding in a number between 0 and 1. So if you're integrating with your AI systems, for example, and it knows that your character needs to move at a certain speed to get to a position, then it can just feed that value to the animation system. And what's more is it allows you to iterate. So you can set it up so when you change an animation, it just reanalyzes. It looks again, how's that animation moved? It moves that point in the graph, and then still you'll get the right results. So when you feed in 4 meters per second, your character will still go at 4 meters per second. It will just use a different proportion of the animations according to how you've changed it. And as I mentioned, runtime performance is also better because using this approach, you actually use fewer animations at once. So another interesting effect is that when you're blending animations, you don't always have to just perform a mixture of the two. You can also extrapolate, and that's useful because sometimes you don't have all the motions that you need. This is particularly true when you're motion capturing. So if we have a look at an example here in this clip, if I come up to here, you can see I'm now able to move forward here at about 4 meters per second and turn at 76 degrees per second. But what if I want to be over here? What if I want to be turning at more like 90 degrees per second or moving a bit faster? Well, I have no animations to blend together. And in fact, you can see this system is saying, well, I'm requesting this value, but actually it can only give me this value because that's the most my animations can do. Well, actually, what I need is another animation over here. But this was motion capture. This was an actor running around at a particular speed. I can't now go and say, find this actor and tell him, you've got to run faster, you've got to turn more. What I need is to create a new animation. But taking this motion capture, giving it to an animator and saying, can you just speed the character up and move him around? That's a difficult task for an animator to do. But actually, we can use the same mathematics that we use to compute the blend here to actually extrapolate out and create a new animation. So I'll show you how that's done. What I'm going to do is tell the system I want to take these animations and use them to create a new animation which I'll put over here. So I'm saying take these animations as input and create a new animation which has this turning rate of about 100 degrees per second and this speed of a bit more than 5 meters per second. And the system can go away and quickly calculate that, so I'll just drop it in this folder. And if I look in my assets now, I should have a new animation clip here. So this is the new animation that it's created. It's done this by mixing together those animations and extending out the range of motion. And in this case, it actually looks pretty useful. In some cases, the basic motion will be okay, but some movements will look a bit wrong. But that's okay. It's just animation. You can take it back into Max or Maya or Motion Builder and change all the detail. But it has the basic properties of motion that you need in terms of, in this case, speed and banking. So just to prove it works, I will add the footsteps in so I can get the timing right for the blends. And now I'll simply add this into my scatter blend. it analyzes it, it's in the right place. I can add that triangle, and now I can go into that space, and I've got you can see the footstep timing is wrong. I need to go and change where I've put my footstep marker probably. But anyway, the principle is it's mixing it. I can see actually I've put the wrong footsteps in, so it's trying to mix left with right and right with left. But the basic principle is there. It's easy to extend and add these animations in. So that's extrapolation. Everything we've looked at so far, though, has been 2D. What if I want 3 dimensions? What if I don't just want blending my speed and my turning angle, but say I also want the character to go up or to go down? Well, if you're using traditional blends, now you need to start nesting even more layers into your blend tree. And your tree of nodes starts to become very, very complicated. With parametric blending, it's pretty simple. It's the same principles as we've seen so far, but instead of a 2-dimensional graph, we have a 3-dimensional graph. And we're blending not triangles, but little pyramids, so that we're blending 4 animations at once. And again, the principle is straightforward, but to be able to use this well, you do need good tools. And because you're building things in 3-dimensional space, what you really need are good automated systems. And that's what we've got in Morpheme. So I'm going to build a new blend again. And in this case, we're going to have our speed and our banking. But I'm also going to add now a climbing variable, say how much we want the character to go up and down. And this time I will add in a 3D scatter blend. So I'll put our banking on X, our climbing on Y, speed on Z, set up the parameters here. And now if I look inside, you can see we've got a 3-dimensional space. And this time I'm going to find a lot of animations. I'm going to take all our animations for walking, jogging and running, drop them all in. The system's going to analyze all of our animations, and you can see it's positioned them here all according to the speed, the banking angle and the rate of climb. And this has now built all of the possible blends that make sense in that space. And I'm able to then run this. So, whoops, let me just get this going. Right, here we go. So, you can see now I'm able to change the speed, the banking, but now if I want the character to go up, the character to go down, it's all in one big blend. And as you've seen, I've not had to do any real work. This is pretty much all automatic. And you can see here, if I go to the debugging, how we're able to move within that space according to the different parameters that we put in. So basically, I've got a completely automatic way of building what would be a very complicated blend. Now, if I spend a little bit more time on it, we're able to get really quite sophisticated results. So in this example, this is built by our animators. And what we've taken here is, as our 3 dimensions, we have the speed, the turning angle, but also the amount that the character's moving sideways, so a strafing rate. And we've built these 3D scatter blends for both one for forwards and one for backwards. And you'll see we've made a very nice grid, and to do this we used the extrapolation function. So we used a bunch of motion capture, and then we used the extrapolation function to get a nice clean grid to reduce the number of animation clips that we needed. We have that for forwards, we have another one for backwards, which is the same thing but mirrored. And then those are joined together in a very simple state machine. So in this example, I have idle and those two 3D scatter blends. And with just that data, I'm now able to run this network. And you'll see here, okay, so now I'm using a controller to change the inputs, but what you can see is I can run and turn and walk and turn, and I can go backwards, and I can also go sideways. And so now I'm able to combine speed, strafing, turning angle, all within one very simple network. It's very responsive. And this whole thing has just 2 blends, 1 idle animation, and a simple state machine. This whole thing can be built in 1 afternoon, and this would now give me all the control that I would need for a basic locomotion system in a game. So 3D scatterblend is really a very, very powerful system. And now we talk about something completely different and look at IK and what we've done with IK in Morpheme 6. So IK is basically a complement to normal animation. So normal animation is what we call forward kinematics, FK, and the position of each bone in the skeleton is determined by its parent. So if I want to know the position that my hand is going to be, I take the position that my elbow has come to, I add on the animation for the next joint, and that produces the result. So you work down the skeleton, kind of rotating the bones to produce the final position. IK is basically going kind of the other way, where instead of just applying a rotation to get a position, you set the position. You say, I need this joint to be here. I know that this joint is here. And you use some mathematics to work out where to put the joints in between, where to put the elbow or something like that. So it's all about using some computation, using some mathematics to solve the positions. And the important thing is, IK is not one thing. There are lots of different techniques for doing IK, but the idea is always the same, that you're working the other way down through the skeleton to using normal animation. Now, what's interesting is once you start integrating IK into blend trees and using IK alongside normal animation. And the easiest thing is you treat IK nodes just like normal blend nodes. Because conceptually, an IK system takes in input animation. It does some mathematics to change the pose of the character, and it produces a new output frame. So you can have these little nodes. And that's certainly the way that we've always worked previously in Morpheme, is we have nodes for doing different tasks. So we have, for example, a foot locking IK node. We have a head look IK node. And each one of these nodes includes some logic to read the animation, perform some mathematics to change the character, and produces the output. And this is really very simple to use. So as a quick example, what I'll do is add a head look onto this. So I have here a simple locomotion system. So this will allow my character to just kind of walk and run around and that kind of stuff. And if I want to add some IK on this to have the character look in different directions, I simply take the output of this network, I find my head look IK node, I take the output animation, and this node takes in a target. I say operate from the spine to the head, and now I'm able to make the character look in different directions, look up and down, and that's layered on top of the animation. So it's pretty simple, very easy to work with, and you can change the effect of it quite a lot. So I can say actually use use more spine in the motion and so forth, and change all the blending. And it's, you know, it's a very straightforward system to work with. But whilst it's easy to use, it has some problems, because if you use lots of these different IK nodes together, they're not aware of each other. So I might have one node that's controlling my right hand and telling me to reach for this point. And so it will perform the operation on my standing move, and I'll pull forwards like this, and that will be good. I then want my other hand to reach. Well, that might operate on the skeleton as well and pull me this way. And I get conflicting results. The two systems don't work together when you've got these independent results, because you take one IK node, you do the solve, you have animation, you take another IK node, it does the solve on its own. And each will only act on part of the skeleton normally. So you can have this situation where they don't interact correctly, and you don't get effects moving across the whole body of the character. The other problem is actually doing the mathematics in IK can be relatively expensive on the CPU, certainly compared to blending animations. And if you have a whole chain of different IK operations to make the character look and then reach and then put his foot in a position, you're doing quite a lot of mathematics for each of those operations. And so it can quickly become too expensive. There's also an issue, which I won't get into too much, which is that you have to set up parameters for each character type separately. So there's an alternative, and that is to use full body IK. So with full body IK, essentially what you're doing is you have a single IK solver that is able to compute the whole character. It doesn't just work on one arm or on just the head or something like that. It can work on the whole body. And the idea is you will choose which of the bones you're going to move and constrain, and which ones you're going to use the animation data for. And then you do one solve, and that computes the resulting animation for the whole body. And full body IK is quite common in offline animation. If you're using Maya or whatever, you quite often have an IK rig on the whole body. It's typically been harder to use at runtime because it's kind of hard to control how it operates. And that's what I think we've solved in Morpheme 6, is finding a way to integrate full body IK into a blend tree setup. So what we've done is, first of all, we abstract out the skeleton to a set of effectors, which is basically more or less a set of the bones that you want to operate on. So you can say, I'm interested in IKing possibly, the head, the shoulders, the arms, and so on. And that's what we then have, is a set of these effectors. You can then place nodes throughout the network, which again are kind of task specific, which are designed to move those effectors in different ways. So you might have one for a head look, which will move the head effector's rotation. You might have one for a reach, which moves at a wrist position to a particular place. And that data is passed through your blend tree alongside the animation. So you do all your animation blending as normal, and separately you're moving these effectors around with IK nodes. And then you have one solver node that you drop in. And that node then converts all of that effector information into the actual animation. So again, hopefully this will be easier when we look at a real demo. So I'm going to start with a very simple fighting network. So what I have here is a simple animation network in which my character is able to perform some basic kind of fighting moves. And you can see we're using debug draw to draw this cross that I can move around. And what I want to do now is use some IK to change the animation so that the character is interacting with that target. So first of all, I put that whole state machine in a node here, and I'm first of all going to add in a head look IK onto this. So here's my FBIK nodes. I'm going to put in our look at node, connect that in, and in here I need to select which effectors I'm using. So the effectors, as I said, are basically just a set of tags on the character. So these are the points that the IK system is going to work on, and you can share these across different characters, which is very important. So my head look is going to work from my spine up to my head, and we've got our target. So if I were to just connect this to the output now, nothing would happen, because all of that node is doing is moving those effectors around. It's not producing new animation. And so to get an effect, what I need to do is add in my IK solver, which will take the effectors and combine it with the animation data to produce the new result. And I tell that I'm now solving for the head. So if I run this now, what we'll see is I'm able to move the target, and we have the character looking at the point. So this is very much the same as when we use the task-specific IK. But now I can start adding other techniques. So one thing that I might want to do with the head look is extend it slightly so that it also controls the hips of the character a little bit. So if I let it control the hips and bring this up a bit, then now what I want is when the character looks around, for it to actually turn the hips as well, so that he's facing the right direction. So if I do this, you can see as he turns, his hips are turning, which is good, but his feet are now sliding all over the place, which is not good. And that's because the look is controlling the hips, but the hips are driving the legs, and that's a problem. So what I need to do now is add some more IK so that I'm IKing the feet to the position coming from the animation data. But of course, because this is full body IK, that's really very easy. What I can do is simply take my IK node here, my set effectors anim, and what this will do is say I want to take the information from the animation and use that to drive where the effectors for the left and right ankles are going to be. So we're holding the feet in position now, as well as making the character look around. So add those into the solver and run it. And what we'll see now is I'm able to look around, and the character's turning his hips as well. You can see his whole body's moving, but his feet are held in position, and in fact they are just following the animation data. So I'm still able to use animation data for moving the feet, but you can see now we're getting a nice effect across the whole body as the character looks around. And so the final thing I want to do is now say I need the character to actually start punching towards this target as well. And this is where the full body IK system is really useful, because the nodes don't have to just be in one place like this. What I can do is actually say I'm going in here into my punching state, and only in my punching state am I going to have the nodes to move the right hand of my character. And in here, what I'll do is take the reach target node, and I'll use it to modify the punching animation to reach towards that target position. And we'll have that go from the right shoulder down to the right wrist. But there's a few more things I need to do, because I don't want the IK to always be pulling towards the target, because then as soon as I run the punch animation, it will just move the target. What I need is to gradually turn on the IK as the punch is happening, and turn off the IK as he pulls back, so that I only gradually get pulled towards the target and released again. And so what we do is we simply use the markup data on our animations to define the period in which I'm turning on and turning off the IK. So I can simply add that information here into my my node, so 1 and 2 for my 2 points. And then the final thing I'll do is tell it how to solve the redundant joints by using this target pose. So you may be familiar with IK sometimes. If I'm punching to this point, IK could solve this way or this way and so on. Now, sometimes lots of programs require you to set a vector to say what angle this is. What we do instead is say, just give us an animation frame, give us a pose to use, and we take the information from that. So I'm actually using part of the punching animation to define what that angle should be, and that's in there. And so finally, I just go into my solver and tell it that I'm now also solving for the right wrist. And hopefully now, when I run this, if I've done everything right, when I punch, he punches towards that target. And if I move the target, you can see we punch towards it that way, and we punch towards it that way. And same if I go up and down. And obviously it's not extending all the way. I'm not going to stretch his arm. It's taking the direction and is using that as the target. And so now with this system, you can see I've now got a character that's able to look in different directions, twist his whole body into that direction, and punch towards a target without creating any new animation data and using just one IK solve. So I'm not having to do 3 or 4 separate bits of IK. This is using just one solve, so it's very, very fast. It's very, very cheap to use on the CPU. So that's our full body IK system. I'm pretty much out of time, so I'll go very quickly through the kind of benefits here. There's still reasons to use the task-specific IK. It's a bit easier to set up. And for some things, it's very, very fast. If you're just doing 2-bone IK, just to move a position, that's a very simple bit of mathematics. It's certainly faster than using full body IK. And you don't have to worry about building your effector rig. The benefits of the full body system, you only have that one solver cost, so it's much more linear. The huge thing though is that the nodes all work together. You're never going to get fighting between the IK systems. You can have everything working towards one goal, so you get much more coherent motion. And although I've not really gone into it much, our rig abstraction means that you can set up your network once, set up your IK nodes once to work across multiple different character types, which is quite a benefit as well. So, let's say I'm pretty much out of time, so I'm going to wrap up there. In summary, as I say, these are 2 major parts of what we put into version 6. Parametric blending, 3D parametric blending, is an incredibly powerful tool for very quickly letting you build 3-dimensional blends, understand them, and have something you can iterate on quickly. And full body IK gives you very, very flexible and dynamic kind of procedural control across your character, again, without having the cost of and complications of stacking up lots of task-specific nodes. So thank you all very much for your time. I would encourage any of you that are interested to look at our website, contact Yoshi here for evaluations and so on. But yeah, that's all for now.
今日はありがとうございます。それで、いろいろ細かな、結構時間なくて、ずっと言っちゃったんで、細かい質問あれば、日本でIGMKK という私の会社が彼らのテクノロジーを皆さんに紹介しているので、私の方にいろいろ質問をメールで投げてください。古畑@igmkk.com、後で来ていただければお名刺渡しますけども、はい、ぜひいろいろ質問してください。実際の、製品もエバリエーションできるように、無料でいろいろ、体験版とか、提供しますので、いろいろ質問してください。
よろしいでしょうか。では、以上でセッションの終了させていただきます。ご記入いただきましたアンケートと同時通訳レシーバーはですね、出口で開始しておりますので、本日はありがとうございました。